Hello everyone. Today we are going to talk about chapter 14, Cosmic Samples and the Origin of the Solar System. The cover picture is an artist's illustration of a disk of dust and gas around a new star. Material in this disk come together to form planetesimals and later on will become planets. First, let's look at what kind of cosmic samples we can get from interplanetary space. First of all, let's talk about meteors. When a fragment of interplanetary dust strikes on Earth's atmosphere, it will start to burn to create a meteor. Sometimes we call meteor shooting star. You can see some meteor can be very bright. And this is a time when a large piece of cosmic material strikes Earth's atmosphere, and we sometimes call this type of meteor fireball because you can see it is very bright. And you may also heard about the meteor shower, that is streams of dust particles traveling through space together to produce a meteor shower. So you basically can observe one meteor after another, although it won't be as that dense as the real rain or real shower, but you are able to, on a certain night, you are able to observe a lot of meteor. Meteor shower is one of the most accessible astronomical phenomena we can observe. You don't really need any astronomical instruments such as telescope, and many meteor shower actually recur each year because they are associated with particular comets that have left dust behind as they come close to the sun as their ice evaporates. Remember when we talk about comets, the evaporate of ices also release the dust previously frozen inside the comets. And those dust, it won't move together with the comets. Instead, it's actually being left in a certain place in the interplanetary space. So as long as Earth actually go into that space, and some of the dust will captured by Earth's gravity and therefore will falling into the Earth's atmosphere and create a meteor. One of the example of the meteor shower is Perseid meteor shower. And this meteor shower is actually associated with comet Swift turtle. And you can see here is a picture of the Perseid meteor shower. And although in this picture you can only see one, I'm going to show you a video footage. You can see multiple meteor in this meteor shower. You can see from the video the meteor shower is actually very beautiful, right? If you missed this year's Perseid meteor shower, fortunately it's actually recur each year. So next year it will also happen around August 11th, 12th, or 13th. Also, there's other meteor showers, and if you want, you can definitely search on the date. And of course, in order for you to observe a meteor shower to see as many meteor as possible, I'm going to show you a video, give you some suggestions on how to observe a meteor shower.
On a typical dark, clear night, away from bright lights, observers can usually glimpse 4 to 6 shooting stars per hour. Now, despite their name, these aren't stars at all, but rather tiny particles of solar system debris, grains of dust or tiny pea-sized bits of matter from the formation of the planets. Earth sweeps up this debris in its orbit about the sun all the time, collecting about 100 tons of this material every day. Passing through denser and denser layers of our atmosphere, these particles heat up, reaching thousands of degrees Fahrenheit and incinerating high above the ground. This causes the brief streak of light known as a shooting star, or more properly, a meteor. When Earth passes near or through the trail of dust particles that were liberated by a passing comet, we may see a meteor shower. With thousands of comets known and new ones being discovered all the time, there are a lot of dust trails looping through the solar system. Now, Earth doesn't encounter all of them, but at specific times of the year it plows through a dust trail, and observers on the ground might see dozens of meteors per hour in the night sky. To see a meteor shower, first look up the peak dates of the major showers and hope for clear skies. Good displays to keep track of are the Quadrantids in January, the Perseids in August, and the Geminids in December. Although these showers are named after particular constellations, that doesn't mean to look only toward those constellations. The names simply indicate where the shower's radiant is located, or the point from which the meteor trails seem to emanate. The meteors themselves can appear anywhere in the sky. Because of this, your viewing site should provide a view of as much of the sky as possible, ideally on a high hill with no tall trees or buildings nearby to block any part of your view. This will allow you to see as much of the sky as you can. And don't use binoculars or a telescope, which will restrict your field of view. Also, make sure you're away from, or at least shielded from, bright lights, which will wash faint meteors from view. Now note that even the best showers can be washed from view by moonlight, especially during the period about a week before to a week after full moon. While there isn't much we can do about the moon's phase, we can time our observations for either before moonrise or after moonset when the moon isn't in the sky. Generally speaking, the recommended time to look for a meteor shower is after midnight and before morning twilight. That's when Earth's rotation has carried us around so that we're looking in the direction of the dust stream. Sort of like driving on the highway and seeing more bug splats on the front window of your car than on the back window. Now, since many meteors can be faint, make sure that your eyes are well adapted to the dark. This usually takes about 20 minutes away from bright lights. And don't spoil your night vision by pulling out your cell phone and tweeting how many meteors you see. Then you'll have to wait another 20 minutes for your eyes to adjust to the dark again. Your best tool will be patience. Watching a meteor shower doesn't mean looking for 5 minutes, seeing one, then going back inside to warm up. To really appreciate a shower, plan on spending a few hours observing. Make yourself comfortable. Bring a lawn chair or a blanket to lie on. While you wait, see if you can make out some constellations. Look for colors in the stars. Watch for satellites. Sooner or later, perhaps when you least expect it, you'll see a brief streak of light flash overhead as a particle of cosmic dust blazes across the night sky. Good luck, and happy sky watching.
After watch the video, I hope you already know what you need to be prepared to watch a meteor shower, and you will be ready for the meteor shower next year or later this year. Not all the meteor will have anything left after it burned through the Earth's atmosphere. If it has something left and reached the surface of Earth, the material will have a different name. We call this meteorites. So, as definition, meteorites are the debris from the space, mostly asteroid fragments that survive the Earth's atmosphere and finally reach to the surface of Earth. Remember, that is the fundamental differences between meteorites and meteors. And depends on how they are discovered. Meteorites are called founts or falls. First, sometime when we have bright meteors like fireballs are observed to penetrate the atmosphere to low altitude. If we search the area beneath the points where the fireball burned out, we may find one or more remnants that reach the ground. So that is one of the way we call falls. We just kind of follow the path of a meteor to find the meteorites. And the second method is called founts. And that is when people sometimes they discover unusual looking rocks that looks very different from the rock from the surface of Earth. And if those rocks, after analysis, turns out to be meteorites, and then we call this type of meteorites how we discovered founts. And the best location to actually discover the meteorites is actually Antarctica ice cap. There's a couple of reasons. First of all, the background of Antarctic ice cap is white. So therefore, it's easier to see the black meteorites actually either on top or kind of half embedded like inside the ice. And the second of all, because extremely cold temperature in Antarctic ice cap, meteorites are actually preserved well by frozen of ice and therefore not subject to too much weathering at another location, for example, the wind erosion or water erosion. So far, the most productive source of the meteor discovery actually is from Antarctic ice cap. In terms of chemical composition of meteorites, they are classified as three types. One is ions. The second we call it stony ions, that is mix of stony material with iron. And the third we call it stones. You can see in this table, actually among all three types, the most abundant meteorites is actually stone type or stoning type. Of the three types of meteorites, the ions and the stony ions are the most obvious extraterrestrial material because on the surface of the Earth, the pure iron almost never occurs naturally. It is generally found here on the surface of Earth unoxidized. That is when iron is chemically combined with oxygen or other mineral ore. Therefore, if you ever come across a chunk of metallic iron, it is either a human-made or a meteorite. So you can see in the table, when you look at the founts, that is when we look at the stones or the piece of material on the surface of Earth looks like a meteorite, and you can see a lot of percentage is actually iron because it's easier to identify. On the other hand, the stony types of meteorites, even if fall on the Earth and due to the weathering or erosion, like water erosion or wind erosion, it will become very similar to the other type of stone or rocks on the surface of Earth. Therefore, it's kind of hard to identify those like stony type of meteorites compared to the iron or stony iron types. And among those three basic types, the stony iron types, the last one, is actually have the smallest percentage. And how the meteorites looks like. And you can see the bottom picture. This picture is actually show a very big iron meteorite. And this meteorite is very huge. It is about 15 tons iron meteorites. It is found in the state of Oregon. And another picture of the iron meteorite is the middle one here. And the stony iron meteorites, you can see one of the example of the picture is right here, is the mixed iron with stony material. And among those three types of meteorites, we believe the most of stony meteorites are primitive objects, because if you remember how the iron was produced is when the objects start to have the what we call differentiation. So therefore, the heavier material sink down to the middle. The stony type, the stone meteorites, are believed to be the primitive objects. It's dating to the origin of the solar system about 4.5 billion years ago. And the most primitive meteorites in the stone type of meteorites, what we call is carbonaceous meteorites. And this is actually give you an example of carbonaceous meteorites. They may date back to even before the formation of solar nebula. We do have a lot of samples of meteorite come from interplanetary space, and most of the time you are able to see them in Natural History Museum. And the primary differences between meteorites and meteor is meteorites are a piece of material reach the surface of the Earth. You can see it is just a piece of iron or rocky material. It is not shining, it's not actually not burning. Instead, meteor are the phenomena when a piece of dust from the space actually enter the Earth's atmosphere. So therefore, as they burn, they actually emit the light, like the flame come together with the burning of this dust. The connection between meteor and meteorites that some of the meteor may not 100% burned up in the Earth's atmosphere. It may lead to some meteorites you may find by following the path of a meteor. Next, let's discuss the formation of the solar system. We have already talked about briefly in the chapter when we introduced the solar system. Unfortunately, we cannot observe the formation of the solar system by ourselves because it happened a long time ago. And the formation process can take up to millions of years, so it is still too long for human history. Even if we're looking at the formation of other stars or the other solar system, it is hard to follow from the beginning to the end. However, at least we know how the solar system looks like today, and we know what is the shape of the entire solar system, and we know what the planets are made from. And so therefore, based on we already know about the solar system today, we can come up with a theory about how the solar system formed. Any theory of a solar system formation must take into account of what we call the three constraints. So that also means they must be able to explain the motion, the chemical composition, and the age of the solar system we are currently live in. Let's talk about this constraint individually. First of all, it's the motion constraint. So we know that all the planets are revolving around the sun in the same direction counterclockwise. And also all the planets orbit around the sun among a disk. In addition, the sun itself and most of the planets also spin or rotate around its own axis in the same direction. And just with some exceptions, for example, exceptions of comets and other like a Kuiper belt object. Any theory that of the solar system formation must explain why everything moves in this way in the solar system. In terms of a chemical constraint, and we now know that the Jupiter and Saturn have approximately the same chemical composition as the star, and dominated by hydrogen and helium. However, the other members in the planetary system have different composition. For example, Uranus and Neptune are made from icy material, and the terrestrial planets are made from the rocky material. And also, you can see the order is that the composition and from the inner solar system to outer solar system is progressively from the metal-rich interplanet through those predominantly made from rocky material, then out to the object with ice-dominated composition in the outer solar system. So therefore, the theory about solar system formation also needs to explain the chemical constraint. And finally, the age constraint. So by the radioactive dating and of some meteorites, we know that those meteorites can date back to about 4.4 billion years old or even near 4.5 billion years old. If they are primitive, and so therefore that should be roughly the age of the solar system. They are primitive just means they actually form together with the formation of a solar system and not chemically changed or altered later on. Now let's just go ahead to look at the theory that explains the formation of the solar system. So the first step is the solar nebula contracts by the force of gravity. The solar nebula was a result of a collapsing of interstellar clouds of gas and dust. As the nebula shrinks, its motion causes to flatten. And as becomes smaller and smaller, as we know from a conservation of angular momentum, it actually start to spin faster and faster. And for you to understand why and spin faster and faster, I'm going to show you two videos to demonstrate that. You can see from this video that the figure skater, one, she folded her arm and leg close to her body, so therefore looks like so she occupies less of space. It actually starts to spin faster and faster. So that is what happens with solar nebula. As it becomes smaller, it actually starts to spin faster and faster. The second video actually I showed you before. I want you again pay attention to the lady's skirt. You can see with a fast spin, the material can have a shape of disc shape. So that's a similar idea as the solar nebula, because solar nebula is actually mostly made from loose bonded gas and dust. As a response to the fast spin, it will be flattened into a disc shape. And the third step is the nebula is become a disk with most of the matter actually concentration near the center. As the center material gather together to form what we call the protosun, and the solid particle condensed as nebular clouds. So you can see that the material inside the disk will kind of condense, form particles. We call them planetesimals. Planetesimals is actually, you can think about that is object or the building block later on to form planets. Since we or nobody actually ever observed the formation of the solar system, how can we know that those steps are actually correct? One of the way is that we can observe in the space there's a billions of stars, or there is still stars still in a formation stage, or the other solar system is still in the formation stage. So you can see the bottom picture. Then we can see some like active star forming region will observe the disc shape from the side. So that is evidence indicate that during the formation of the solar system, there's the time that the solar nebula is a disc shape. And other than that, we also observe other solar system like formation, the system around other stars. You can see especially this one is a very obvious, it is a disc shape with a center star, and you can see there's still a lot of material left inside the nebula around the star, but you can see clearly there's already some gaps. We believe those gaps are created by the newly formed large planets. It's trying to clear its orbit. And what happens for those planetesimals? You can see from this picture that there's a lot of planetesimals. So therefore, there are a lot of collision between them, and there are always, of course, a merge between them as our planetesimal and collide and merge with other planetesimals. They will grow up in size and finally form our bigger planets later in our solar system. The process I just described is similar to how you make cotton candy. You can see as the planetesimal collect more material, it will grow bigger and bigger in size, and later on will form big enough to become a planet. And then what happened to the planet? As the material actually attracted by the force of gravity into the planet, this infalling material actually able to heat the planet, therefore leading to their differentiation. When the planet is heated, all the like rocky material, for example, for the Earth, the interior, it become molten or liquid. So therefore, the heavy material like iron can go all the way to the center, left the lighter material like rocky or silicon material near the surface. It may not be easy to understand why the accretion of infalling material can heat up the planets. I want to use a simulation to explain that. You can see this is the state of matter simulation I showed you before when we talk about density, pressure, and matter at the beginning of the semester. You can see if what happens if we increase the temperature, what happens? Of course, the molecule will start to move faster and faster, right? So what we talk about the temperature, fundamentally the definition of temperature is a collective of the motion or kinetic energy of an individual atom or molecule. You can imagine under the force of gravity, for example, if you drop our object to the ground, the object will move faster and faster, right? So therefore, as the object moves faster and faster, collectively what we observe is that the temperature is actually become higher and higher. So therefore, those two terms, the fast motion of a molecule and a high temperature is basically equivalent. That is why when the materials are falling under the force of gravity and it moves faster and faster, that also means that the temperature actually becomes higher and higher. And the difference between the giant and terrestrial planets is that the giant planets, because they are large mass, they have large force of gravity. They were able to attract and hold gases from a solar nebula, because a gas are loosely bound material, so they actually can easily escape away the force of gravity of a planet. And what about the terrestrial planet? The terrestrial planet, due to its smaller size, therefore the smaller mass, so there has less amount of force of gravity. So therefore, they are mostly only made from the solid or rocky or iron material. What kind of material, if it's a planet can hold gas or not, also depends on the temperature. You can see as the planet is close to the sun, from the Mercury, if you remember, Mercury is a probably rocky material. This interior has mostly a very big iron core, and it has no atmosphere, because at the location of Mercury, the gas molecules are all move very fast because of high temperature, right? We talk about high temperature means the gas molecule move fast. Mercury is also our smallest planet. It cannot hold up those atmosphere or gas. Therefore, as a result, you can see Mercury is mostly made from metal with some of silicon or rocky material. And as we progress, then you will see that the planet start to pick up some lighter material like silicon, the rocky material, and as we go on, as we go further and further away to the solar system, with a decrease of temperature, it is easier for the planet actually to keep the gas around. Of course, the mass or the gravity of planets is also a very important factor to take into consideration. The reason you could observe this trend because the first materials able to form the solid grain were the metal and the silicon. So because they have what we call higher melting point, so they can form solid form even at a relatively high temperature. As we progress further and further away from the sun, you can see sulfur compounds, right? And as like which is iron sulfide. And as we go further and further away with even lower temperature, allow the oxygen to combine with hydrogen, so to condense in the form of water, as well as hydrogen interact with other type of element, for example, nitrogen and carbon, to actually form the compounds of ammonia and methane. And if you think about at the beginning of the formation of the solar system, the solar nebula should have all kinds of material, like almost evenly distributed. However, due to a high temperature close to the sun, those material will evaporate easily, can easily escape the inner solar system, and they can only survive in the outer solar system with a temperature that much lower. And right after the planets form, the solar system is not our clear or peaceful place as we are right now. Right after, there is still a violent impact, because at that time, there was still a lot of kind of debris left. Remember, those planetesimals, they are still not become a part of a planet, so they are still left inside their orbits of the inner solar system and outer solar system. So therefore, there is a period of a violent impact. And the violent impact may result that at this stage that Mercury, part of its mantle and crust, being stripped away by the big impact, as well as Moon. And if you remember, we talked about Earth-Moon. The giant impact theory is talking about a mass-sized object impact on Earth, then some material from Earth's mantle, and later on forms the Moon. And the violent impact is not always bad because the gravity of a giant planet is very strong. So therefore, even some icy, like debris or planetesimal in the outer solar system can speed up when it's approaching to the giant planets. So therefore, there is some comets actually were able to strike or impact on the inner solar system object. And as a result, a lot of debris striking the inner planet was actually ice-rich material. And very interestingly, if you look at this image, you can see in the location with Earth, it is still too close or too hot for the water to form, right? So therefore, we actually believe a lot of the water on the Earth actually come from the comets, bring by the comets during this violent impact period, when a lot of comets actually come from the outer solar system, impact climb with the Earth, and therefore bring the water and to the surface of the Earth. And of course, at the same time, we believe Venus as well as Mars and Mercury, they all have the impact by the comets. So therefore, they may also beginning with some water. But we already talked about that Venus due to its hot temperature and Mars due to its too low temperature. So therefore, there's no liquid water. But definitely on Mars, if you still remember, there's evidence of a past water flow, and we definitely found a lot of ice actually underneath Mars' surface. And what happened after the violent impact period? So after a few billion years of violent impact, so the most of the debris, they were either falling into the big planet, become part of it, or they are just swiped up or ejected. And therefore, some of them ejected into the Kuiper Belt and outer cloud, and some of them aggregate between the orbit of Mars and Jupiter, which later on formed the what we call asteroid belt. So leaving the only asteroid and a comet remnant surviving to the present. But again, even if they survive, they are not randomly distributed in the solar system. Asteroid primarily in the asteroid belt and a comet in the Kuiper Belt and outer cloud. In order for you to better visualization the solar system formation, I'm going to show you a video with the simulation to show how everything works during the process of the solar system formation.
In the past few decades, our spacecraft have visited many exotic locations in the solar system, including icy comets that have orbited the Sun since the planets were still taking shape. We have explored relatively tiny asteroids, ancient rubble piles held together by weak gravity. And we have found that the largest asteroids resemble the building blocks of planets themselves, all of which suggests that these objects offer clues to how the planets formed. And we have even found evidence for a violent rearrangement of the planets. Computer simulations allow us to reconstruct the formation of our solar system 4.6 billion years ago. We use the laws of physics to create these virtual experiments in order to figure out how planets took shape. After the Sun ignited, most of the material around it had flattened into a disk of gas and dust. We can zoom into a simulation of a portion of the thin disk, a small piece of the universe in a box. Here, a dense swarm of objects clump together to form what astronomers call planetesimals. This simulation addresses how planetesimals form from much, much smaller particles, the size of pebbles. Pulled together by gravity, some planetesimals formed the planets, while others became asteroids and comets and dwarf planets. As the planets accreted, they carved out gaps in the disk, but the solar system remained quite cluttered. If we look at the orbits of the planets and accelerate the passage of time, so 1 million years pass by every 10 seconds, we can watch how the debris cleared. In this simulation, the giant planets, Jupiter, Saturn, Uranus, and Neptune, shift their orbits, and many unlucky asteroids and comets and dwarf planets get kicked out of the solar system. The migrating giants wreak gravitational havoc. The distribution starts out quite flat, but as most small objects get tossed out, others settle into stable orbits that allow them to coexist safely with the planets. But their orbits aren't as flat as the original solar system. Instead, they follow trajectories far above and below the plane of the planet's orbits. Today, the orbits of Pluto and other Kuiper Belt objects show exactly this pattern. The tiny icy worlds that inhabit the outer reaches of the solar system provide evidence for an ancient interplanetary transformation.
You can see from the video exactly how those debris are actually cleared out by the giant planets. And so therefore, during this process, also the giant planet's orbit is not very stable as it's clear out the debris. But for nowadays, everything is actually become stabilized. Therefore, now everything, almost everything is already in the location it should be and orbiting around the sun. And we already know there are billions of stars in the universe. And if we think about the sun is not unique, that also means there will be planets orbiting around other stars, maybe more than us or fewer than us. And you may think about with the advanced telescope and detectors we have today, we can directly image those planets around the star. And we call this planet exoplanets. However, this has proved extremely difficult. There is a couple of reasons. First of all, most of the stars are very far away from us. The star by itself is just a bright dot, let alone the small planet orbiting around the star. Remember, planets, they won't emit their own light, and they're extremely small compared to the star. So therefore, it's almost impossible for us to directly image the planets. And also, as those exoplanets orbiting around their parent star, even they have a little bit faint reflection of light from their parent star, but the parent star's light is so overwhelming, so basically they can lost visually in the brilliant glare of the star they orbit. We know already for a very long time there should be the other planet orbiting around other stars. It is not until 1995 the first planet circling a distant solar type star was announced. It's because it's almost impossible to directly image them. That's also indicate that if you ever see any exoplanet picture, those are not a real picture of exoplanet. They are actually the artist's illustration based on the data they gather. So far, we did not have any clear image of exoplanets, and such as the image of, for example, the Mercury or the Earth or the Mars. By the way, the exoplanet is super interesting. One of the reasons that the efforts for searching for life inside the solar system, especially intelligent life, does not come up with a very good result, right? So far, the moons, the planets we visited, there's no evidence there is intelligent life. So one of the reasons scientists are extremely interested in exoplanets, because imagine there is a billions of stars. Each star can have a few planets, even tens of planets orbiting around that. There must be some like Earth-like planets, maybe habitable for life. We are most interested in exploring the exoplanets, also connect with to searching for life in the universe. So let's talk about the two of the most popular technique to detect the exoplanet. The first one we call it is a transit photometry. So what happens that is, one, the exoplanet orbiting around its parent star. When we look their overall brightness, you know, even exoplanet is small, is faint, can reflect some light from their star, but they still have some of light, even though we cannot really see it directly. But what happens is that when the star and exoplanet, they are not overlapping, the total brightness you observed is the brightness of a star plus the brightness of exoplanet. However, when the planet is orbiting and to the front of a star, what happens is that the planet actually covers a part of the star. Even if it's still a very small portion, we're able to detect the decrease of the brightness. So we'll know that there is something actually in front of it. And maybe a black dot, it is actually a shadow of our exoplanet. This is actually a very popular technique for us to detect the exoplanets as well. By using this way, we can also estimate the overall size of exoplanet, because we know that the larger planets will result a larger decrease of brightness, and the smaller planets will result a smaller decrease of brightness. And the second method is using the Doppler effects. And when there's a planet orbiting around a star, usually the star's motion will affect by the planet. The star is actually not exactly rotate around its own axis at exactly its location. More precisely, if you look at the star will wobbles because the orbiting of our planet. So instead, the star looks like it appearing to kind of move around a circle, instead only orbiting around its own axis. As the star wobbles, sometimes the star you can see is actually kind of moving towards us. So therefore, the spectrum we observe from a star will have what we call the blue shift, the Doppler effects. Moving towards the observer will have blue shift, means a higher frequency. And when the star moves to the other side, the star is actually wobbles in this small circular orbit, so it's moving away from us. So we'll observe that the spectrum will have the right shift, longer wavelengths, therefore lower frequency. And by looking at the motion of the star, like relatively how much blue shift and how large is the red shift, we can estimate the mass of the exoplanets. Remember, we talked about that the reason why we can estimate the mass, because the force of gravity is a cause of motion. Therefore, by observing the motion, we'll kind of extrapolate back to calculate the mass of the object in this system. That means the exoplanet and the star. So by using these two, primarily these two method detecting technology, so far we actually can identify thousands of exoplanets. Remember, those are both indirect detection technique. If you take a look at this graph is pretty much show you how many exoplanets actually are also in terms of the mass are observed by these two method or detection technique. The gray dots are the exoplanet identified by the radial velocity technique, and the red dots are the ones identified by the transit photometry technique. You can see majority exoplanets we identify are big, right? So it is not hard to imagine because the bigger or the heavier the planets, it's easier for us to observe the decrease of the brightness, or easy to us to detect the Doppler shift of the star, because it can influence star more than the smaller or lighter planets. So therefore, you can see majority of a planet we observe are the similar size or even larger than Jupiter. However, with a development of the technology that the advanced instrument can detect even smaller change of brightness or smaller shift of the frequency, we're able to detect planets closer and closer to the size as well as the mass of the Earth. As we discover more and more exoplanets, we found that some exoplanet systems actually are quite different from what we have in the solar system. For example, a few percent of exoplanet system, they have hot Jupiter. That means the Jupiter, instead in the location further away from the sun, is actually very, very close to the parent star. So because we believe at that location it should be have higher temperature, that's why we call it hot Jupiter. And like massive planets orbiting close to their star. And also some of exoplanets are actually in eccentric orbits, unlike what we have in the solar system. So you can see when you look at other star system or exoplanet system, they looks quite different. Some of them are actually look quite different from our solar system. And also we talked about that with the advance of technology, we're able to detect smaller and smaller planets, such as terrestrial type rocky planets, because they're small, so they're even harder, even use indirect technology, they are harder to detect. And we actually believe that in our own Milky Way galaxy, we have tens of billions of such Earth-like planets. Maybe on one of them, there's an intelligent life as a human being. So that is one of the reasons exoplanet exploration is one of the hottest field in the astronomy research. And you can see this picture, it is again, it is a not real image. It is artist illustration of the Earth-like exoplanets we already discovered. And also, as we mentioned that, there's a lot of differences of the actual planet system compared to our own solar system. For example, one of the differences is that you can see we have no planets actually between the size of Earth, Venus, and Neptune and Uranus. But in the actual planet system, we do see a significant amount of the planets actually between the size of Earth, Venus, and Neptune and Uranus. So actually fill the gap of the planet size we observe in our solar system. If you're interested in exoplanet, I definitely suggest you to go to the NASA website, Exoplanet Exploration. It actually have a lot of information. In 1995, we actually confirmed existence the first exoplanet. Now, to most recent, this number is over 5,500. And of course, this number will keep rising as time goes by. And you can see definitely on this website, there is a lot of all news. You can look at all the news about actual planets, and you can read detail of actual planet exploration program. And also explain what is actual planet. And they actually divide actual planet into a different subcategory, like gas giant Neptune-like or mini Neptune, super Earth or terrestrial. And you can see there is also a lot of information, and then you can learn about different missions to discover the actual planets. Later on, you will learn that a lot of actual planets are actually named as Kepler with a number. It's because Kepler mission is a primary mission to discover actual planets. And you can see there's also a lot of multimedia resources you can use to understand the actual planet better. So other than the searching for the life in the actual planet, we also get other benefit by studying the actual planet. So understand the differences of actual planet system compared to our own solar system, we can understand the detail of the formation of our own solar system. For example, the discovery of hot Jupiter also indicates that giant planets previously formed in the location further away to accrete the ice and the gas material, then they actually can migrate inwards from the place of the formation, so they can be closer to the star. And I want to share with you 2 videos from NASA Actual Planet Exploration website. It's very interesting. It will give you a little bit more details about actual planets.
You're probably familiar with the major types of planets in our solar system. You know, there are some smaller, rocky planets and some giant gas planets. The rocky, or terrestrial ones, are closer to our star, the Sun, where it's much warmer, while the giant gas planets are farther out in the cold. But what about other planet systems we're finding out there among the stars? For the most part, they don't look a whole lot like ours. Turns out, there doesn't seem to be a typical arrangement for planetary systems. Yep, all planetary systems might be weird. Most other systems of planets are certainly arranged differently. Sure, there are lots of planets out there the size of Jupiter and Neptune and Earth, but their Jupiters and Neptunes can be way closer to their stars than ours. Some as close or closer than the orbit of Mercury. So scientists who study these exoplanets, planets outside our solar system, find themselves using terms like hot Jupiters and warm Neptunes. Plus, there's a whole range of exoplanet sizes, from much smaller than Earth to even bigger than Jupiter. To help describe what weight class each of these planets belongs to, we often refer back to the different planet types in our solar system, using terms like mini-Neptunes and super-Earths, or super-terrestrials. We're constantly learning more about exoplanets, and our ideas about them are changing as we go. Ideas about how these different planet types relate to each other, and what their variety can teach us about our own weird little solar system.
And also, I want to share with you another video from NASA Exoplanet Exploration website to actually compare other exoplanets to the Earth.
Earth is awesome. What would be even more awesome if we found another Earth, or a bunch of Earths? That's one of the things we're looking for at NASA as we study exoplanets, planets outside our solar system. But maybe searching for a planet similar to our own, where conditions might have led to an entirely unique origin of life, finally telling us that we're not alone in the universe? Maybe that's not your thing. That's cool. Maybe you're more interested in just how weird exoplanets can be. We think there are entire worlds covered by deep oceans, water worlds. Not weird enough for you? Okay, how about planets covered entirely in oceans of lava? There are egg-shaped planets, worlds that orbit so close to their stars that they're pulled by gravity into a lopsided shape. And there are planets where conditions might be just right for it to rain things like glass or even rubies and sapphires. There are planets that orbit pairs and even groups of stars. Imagine having 3 or 4 suns in the sky. On the opposite end of the spectrum, there are the loners, rogue planets wandering out in space with no star to call their own. There are even planets that orbit dead stars, stars that exploded long ago and left behind a rapidly spinning core called a pulsar. Some of these pulsar planets could be among the oldest in our galaxy, pushing 13 billion years. Such planets would have witnessed most of the history of the universe. Sadly, nearly all of it without tacos. Now, we think, though we haven't found one yet, that there probably are exoplanets pretty similar to Earth out there. But in the meantime, there are absolutely tons of weird, wondrous worlds in our galaxy.
And I hope you found the concept of exoplanets a very exciting topic. And definitely we'll have more information about exoplanet later in the near future. And maybe one day, NASA will announce that we can find life on one exoplanet. And we are looking forward to that day. As we are approaching the end of discussion of the solar system, let's take a look at how the planetary evolution happens. So after the solar system becomes stable, so after the planets clear out all the debris from the solar system to confine them into the asteroid belt, Kuiper belt, and outer cloud, what happens to the planets individually? And as we already talked about when we discussed Venus, Earth, and Mars, and how they actually evolve differently, especially their atmosphere. And now I want to focus on the 3 aspects. The first one is atmosphere. Then we'll talk about geological activity. And finally, we'll talk about elevation differences. And we believe for the planets or the moon's atmosphere were formed by a combination of gas escaping from their interior. For example, the volcanism will bring a lot of gas from interior. And we talked about impact of the volatile rich debris, such as comets actually bring some like water, methane, and like ammonia from the outer solar system. So you can imagine that it's pretty much how the planets have at the beginning. As we already talked about, the mass and temperature will lead to different evolution paths. For the Mercury, which is actually closer to the sun because of small size and high temperature, all the gas can actually escape from Mercury because it's just too hot, and Mercury do not have strong gravity to keep those gas around. And if you compare Venus and Earth, and because Venus is a little bit hotter than Earth, it's closer to the sun, so therefore it does not really have liquid water. So most of carbon dioxide are cooked out. Basically, like the high temperature force carbon dioxide to come out from rocks. So therefore, Venus has very dense atmosphere with full of carbon dioxide. And unlike that, the Earth also at the beginning has a lot of carbon dioxide, but because the Earth is right at the perfect location in the solar system, so the temperature is not too high or too low. Therefore, the liquid water can survive on the surface of Earth. As a result, with the life up here on the Earth, the plant life actually changed the atmosphere of Earth a lot, basically, which absorb carbon dioxide and replenish the atmosphere of the Earth with a lot of oxygen. And unlike Venus and Earth, Mars is a little bit further away from the sun, so therefore Mars actually, because it's a low temperature, a lot of the gases actually were not able to remain in a gas format. For example, Mars actually have a solid carbon dioxide, right? So as a result, because it's a cold temperature, a lot of gas are actually frozen onto the surface, lead to Mars have, although still mostly carbon dioxide, but it's a very thin atmosphere. And other than those planets, and we know that the outer solar system, the gas giant, actually have a lot of gases. And one thing standing out is Titan. It's the only like a moon in the outer solar system actually have thick atmosphere. And the difference is that the Titan's atmosphere is contained primarily of nitrogen, because Titan's location is still much further away from the sun. Although Titan is the largest moon of Saturn, at that cold location, you can see water will be in the form of water ice as hard as a rock, and methane will be in a liquid form. So you can imagine it's not surprisingly that carbon dioxide will also in the solid form. So therefore, the only form of like material can be remain as gas status is actually nitrogen. And in terms of geological activities, and remember we talk about geological activity are closely related if a planet have like a molten interior. So we believe during the bombardment period and the initial formation of the planet, because the gravity will able to heat the interior by the accretion material falling into the planet. So that is step of differentiation, which happens very early. And due to the differentiation, and iron and heavy metals are concentrated at the center, left with a lighter crust and to the surface. And later on, that actually lead to the formation of a solid crust. And there's a bombardment period. That means they are still clear out of the debris. There's still a lot of debris hitting the surface. And due to the bombardment as well as the interior heating, and there is a widespread volcanism, and the planet cools down, the volcanism actually being reduced. And as the crust becomes solid and is still like a mantle, still kind of molten form, there's a possible plate tectonics. As mantle solidified, it's basically the end of tectonic activity. And the final state is everything is cooled down. The interior is 100% solid, so therefore there's no geological activity. You can see how fast the planet can go through this process really depends on its mass. And the higher mass of a planet, then that means it will maintain the interior heating for a longer period of time. So therefore, it will take a longer time for it to go all the way to the last step. If you compare the terrestrial objects, like 4 terrestrial planets plus the moon is the smallest, and we believe at the current status, the moon is already at the last stage. The interior already cools down, there's no activity. And you can see for Mercury, the mantle solidification just happened, and that marked the end of tectonic activity. But you can still see some evidence of past tectonics. And for Mars, and we know there's a possible plate tectonics like Valles Marineris, right? And for 2 bigger ones like Venus and Earth, and the volcanism is not that heavy as past, but it's actually, especially for Earth, we actually have plate tectonics. The larger the planet, the slower they will go through this process. And finally, let's talk about the elevation differences. We're going to compare the highest mountain, Mars, Venus, and Earth. You probably already know that Mountain Everest is the highest mountain on the surface of the Earth. But it is not the highest mountain on the terrestrial planet. Maxwell Mountain is the highest mountain on Venus. And the highest actually mountain in the solar system is actually Olympus Mons. Olympus Mons, if you remember, that is a mountain on surface of Mars. Do you notice that the highest mountain is actually happen on very small terrestrial planets? The high mountain can be supported on smaller planets because it has less amount of gravity. You can imagine the effects of gravity is to pull everything down to the center. So as the growth of the height of a mountain will need to fight against the pulling down of gravity. So therefore, it's easier to have a smaller planet with less amount of gravity to have higher mountain. You can imagine as the planet become bigger and bigger, the mountain will become lower and lower. As a result, their surface feature will become flatter and flatter. That is primarily due to the force of gravity. And the force of gravity can kind of shape the elevation on the surface of a terrestrial object is also and result another effect. If you look at the sizable moons, like the terrestrial planets, they pretty much have the spherical shape. If you still remember that we talk about asteroid and comets, their shape is irregular. The reason is also because of gravity. The gravity, if it can, usually puts an object into the most what we call the efficient shape, where all the outside points are basically equally from the center. All the planets and the larger moons are nearly spherical is because the force of their own gravity pulling them into a sphere. But the smaller objects, the more irregular they can have. Because as you can imagine, rocks is also pretty strong material. For the smaller object, if gravity is not strong enough, it may not able to pull down the rock efficiently. For the rocky bodies, such as asteroids, the moons of planets, the limiting diameter is about 400 kilometers. So the object larger than the 400 kilometer will be approximately a spherical shape, while the smaller ones can have almost all kind of irregular shape. So basically, at the end of this chapter, we already finished talking about our own solar system. That is all what I want to discuss about chapter 14. In chapter 14, we first talk about the cosmic debris, like meteors and meteorites. Then we discuss the formation of a solar system with the formation of the major planets. And next, we talk about the other planetary system, especially put emphasis on the actual planet, their discovery technique, and what the differences between the actual planet system compared to our own solar system. And finally, we summarize the chapter by looking at the planetary evolution and how planets evolve differently and right after their formation in the solar system. You can see the mass as well as their distance from the sun resulted to the temperature differences actually contribute a lot to the different evolution paths of the planet.